Lesson 9, we're going to be talking about gases. We are going to talk about the properties of gases, describe the relationship between pressure, temperature, and volume, and then learn about Boyle's law, Charles' law, Avogadro's, the Guy-Lussac's law, combined gas law, and ideal gas laws. So lots of equations in this chapter. As you can see, along with the new vocabulary terms, there is a large set of equations. Luckily for us, most of these equations can be derived by just remembering this bottom equation here. So first we're going to explore the properties of gases, and we're going to compare those properties to that of solids and liquids. So starting with the diagram on the bottom of the slide, the first cylinder is representing a solid. You can see by the stacked structure. The second cylinder, the molecules are moving to form the shape of the container, so that's the liquid. And then the last container is a gas because it is completely filling all possible space within the container. So let's look at the differences between density, compressibility, and fluidity of solids, liquids, and gases. So starting out with solids, solids are the most dense out of the three. Liquids then are going to be second there. And then gases, of course, are the least dense of the three. Now, as far as compressibility goes, so trying to compress a solid, that's going to be pretty difficult. They're already stacked structures with the molecules pretty tightly knit in most cases, so they're not going to compress very much. The same goes for liquid. It's pretty hard to compress a liquid smaller than it already is. But gases, however, those can be compressed very easily. That's where high pressures come in, right? We can compress gas under high pressures in tanks, for instance. Now let's look at fluidity. So for a solid, notice in the picture, the solid is stacked in a square or rectangle, depending upon your perspective. So they are not fluid, right? They're not going to flow, move. They are stacked structures. Now, as far as a liquid goes, notice the liquid is spreading out to form the same shape as the container. And if you think about liquids, the very definition of them is fluidity, right? Water, it's movement, fluid. Gases, same thing, very fluid. They go one step further than a liquid because their density is so low. Instead of just forming along the base of the container, they can spread out to the entirety of the container. So now looking off to the side, just some pictures to show the compressibility differences between a gas. So the gas being on the top, you can tell much easier to compress it. You just need high pressures to do that. Or high force, both works into play. And then you can see the compressibility of a solid with this carrots here, right? It might be a little bit smaller when you vacuum pack it, but not much. Since we're talking about gases, let's define pressure because we're going to be talking about pressure a lot in this chapter and even calculating pressure. So pressure is a force exerted by gas molecules as they collide in the surfaces around them. So whatever container the gas molecules are in, those gas molecules are constantly moving. And as they move, they hit the sides of the container. So how often they hit the sides of the container and the amount of force they hit the sides of the container with is going to contribute to the pressure. So for instance, if you were going to make that container smaller and still have the same amount of gas molecules in there, you're increasing the pressure because now that you made the container smaller, those gas molecules are still going to move at the same speed, and they're now going to hit the sides of the container more because there's less surface area, making the pressure increase. So as you can guess, to calculate pressure, the equation we would use would be force divided by area, right? It's the force applied and the area that the gas molecules have to move around in. So we measure pressure with several different units. We have atmosphere, represented by ATM, pascals, which we often convert to kilopascals, so kilo being a metric conversion, millimeters of mercury, as well as torr. So we'll see some conversion factors so that we can convert between these different pressures, unit pressures. Well, now, how is pressure measured? Well, pressure is often measured by a barometer, as you can see in the picture off to the left. So for a barometer, how does it work? Well, it's actually how we got the units of millimeters of mercury to begin with, because for a barometer, you have mercury in a vacuum sealed tube. And how we can read the atmospheric pressure is, well, the atmospheric pressure is the pressure of the gases all around us, essentially pressing down on us. So with that atmospheric pressure, it's pressing down on the mercury, causing the mercury to rise up the tube. So they measure that amount of mercury in the tube in millimeters, thus coming up with the units of millimeters per mercury for pressure. Now, with those equations that you saw on one of the original slides, there's more variables than just pressure in those equations, right? There's also going to be volume and temperature. So we need to know the common units that we need to use in those equations, um, as well as some conversion factors for converting pressure, because that's going to be our main new unit since we're talking about gases, our main new variable. So let's just go through this table one by one. So we have mass. So anytime we're using mass, most commonly it's going to be in grams. This is the unit that we need it in. Now for amount, that's going to be moles. And we represent moles by the letter N when it's in an equation. So that's the variable representing moles. Now for volume, volume is represented by the letter V in the equations. Now when we're using volume in these equations, we want the volume to be in units of liters. So it's important, if it's not in liters, we'll most likely need to convert it. Now for pressure, pressure represented by the variable letter P, and the units we want to use in the equations is going to be ATM or atmospheres. So if it's in any other unit, we'll probably need to convert it. Now notice there is a large list of pressure conversion factors over here. So we can be given pressure in pascals, in bars, in atmospheres, millimeters of mercury, or in torr. So there's our list of conversion factors to help us get there. Now temperature, this is a little bit new for us. Temperature in these equations, it's represented by the letter T, so that's not the new part. The new part is we need it in Kelvin. When we use these equations. So before, we generally kept it in degrees Celsius. For instance, with the heat equations, the Q is equal to MCAT, we always kept those in degrees Celsius. But for the gas equations, it needs to be in Kelvin. So let's go over the equations that are derived from this master equation that I pointed out on that equation slide. So this master equation, you'll notice, has pressure, volume, temperature, and then that N stands for moles. Okay, so it has 4 different variables in it. So these laws that we're going to go through are just using parts of that original equation. So let's start with Boyle's law. So Boyle's law is just focusing on what is happening with pressure and volume. So it's keeping temperature and the amount, the molar amount, constant. So the equation then is going to just include the variables that have pressure and volume. So we're just using the top parts of the equation for Boyle's law. So if you can memorize this big equation, you can transform it depending on the parts that you need. Now let's look at Charles' law. So for Charles' law, it's temperature and volume that we're focusing on. So we're keeping pressure and molar amount constant, so we're just using those parts of the equation, as you can see here. Now looking at the Guy-Lussac's law. So for the Guy-Lussac's law, it's temperature and pressure that we're focusing on. And those are directly proportional, which we'll get into because we're going to look at all of these laws individually and do some practice calculations with them. Now Avogadro's law, you can guess, Avogadro defined the mole, so it's going to be moles for sure. But the other variable that is included in Avogadro's law is volume. So you can see we're keeping pressure and temperature constant when using Avogadro's law. So Boyle's law, we're just focusing on pressure and volume. So pressure needs to be in atmospheres, volume needs to be in liters. Now you'll notice that there are pressure and volume variables on both sides of the equal sign. So P1 and V1 are representing the initial pressure and volume. P2 and V2 would be the final pressure and volume. Now that means we're keeping constant temperature as well as molar or the amount. So when we use this equation, we'll see that pressure and volume are inversely proportional, meaning that if one goes up, the other goes down. So you can see that in the diagram off to the right. So as the pressure increases, so as the pressure goes up due to the added weights, the volume is going down. So it used to be a much greater volume, if you can see under the P1. So large volume, low pressure. P2, high pressure, low volume. So that's the purpose of the diagram off to the right. So let's try a practice problem. So for Boyle's law, remember we're just using the highlighted portion of that master equation. So you would get a question similar to this. What is the pressure of a gas initially at 1 atm and the volume decreases from 0.6 liters to 0.05 liters? So plugging those variables into the equation, so you'll see that we have an initial pressure of 1 atm, so that went in for P1. Now they have the volume changing and they're asking us to solve for the final pressure. So the initial volume is 0.60, so that went in for the VI. The final volume is 0.050, so that went in for the V2. So now we just need to rearrange the equation to solve for final pressure. So when we do that, we calculate it out and we get 12 atm. Notice we're keeping with significant figures because there's two significant figures in all the numbers given to us in the question itself. And the units are atmospheres because that was the original units of the pressure as well. Let's do one more and feel free to pause it and try this one on your own. So we have a sample of oxygen, occupies a space of 5 liters at 1.5 atm. What pressure must be applied to compress the gas to a volume of 1.50 liters? So this is very similar, right? We have the volume changing, they give us the initial pressure and they want the final pressure. So once again, we're using the Boyle's law equation with just pressure and volume included. How I like to approach these problems is by making a list of knowns and unknowns, as you've probably noticed from in class. So my P1 initial is 1.5. That has a volume of 5 liters, so that's my V1. P2, the final pressure is what I'm solving for, and then they did give us the final volume. So now I can plug those in to the equation above, solving for P2, and I get 5 atm. Now I notice I don't have the correct sig figs on here. So the correct sig figs would be 3 significant figures since that's what they have for all of the numbers in the question. So the correct sig figs should be 5.00 atm. Now I want to point out that this is showing the inverse relationship between volume and pressure, meaning let's look at what happened to the volume. So the volume started at 5 liters and it went down to 1.5. So the volume decreased. And remember, we said there was an inverse relationship. So if one goes down, the other has to go up. So since we saw the volume go down, that means we should see the pressure go up. So this is a little check you can do when you're solving to make sure you rearrange the equation correctly. So in this case, the pressure started at 1.5, and we just said it should go up since the volume went down. Did it go up? Yes, it did. It went up to 5. So Charles' law is utilizing volume and temperature. So we want volume in liters once again, like we did for Boyle's law. And now for temperature, we want in Kelvin. They often give it to you in Celsius, so make sure you're converting that by adding the 273.15. to the Celsius amount to convert it to Kelvin. Now, what we see with these variables is that they're proportional, meaning if one goes up, the other will also go up. So if you increase the temperature, you will increase the volume, and that's what the diagram off to the left is showing. So we can see we have T1, a very small flame, with this corresponding V1 volume. Now, if we increase the flame, increasing the temperature, we see the volume also increase, making those variables proportional to each other. If one goes up, the other goes up as well. Notice pressure is remaining constant. We're not changing that at all. Neither are we changing the molar amount, the amount of the gas involved. So let's do a practice problem with Charles' law. So from the master equation, we're just using the highlighted portions, volume and temperature. So the question we're looking at here is giving us an initial volume of the gas, 0.6 liters, and it is showing us what the temperature change is. So the temperature is decreasing. So remember, these are temperature and volume are proportional with this equation. So since the temperature is going down, we should see the volume also go down. So that means our answer should be less than 0.6 liters. So let's look and see, plugging those values into the equation will look something like this. Rearrange that equation to solve for V2, and we get an amount of 0.53 liters. So the temperature went down, as did the volume. Checks out. Let's look at another example utilizing Charles' law. Feel free to pause and try it on your own. So we have a balloon filled with helium, volume of 4,000 liters, big balloon, at 25 degrees Celsius. So they're asking what would the new volume be if we raised the temperature to 50. So notice the temperature is going up. So that's your first clue that the volume should also be going up, because with Charles' law, volume and temperature are proportional. One goes up, so does the other. So first step is to convert the Celsius to Kelvin, because you do need temperature in Kelvin in order to solve. Then you'll rearrange the equation to solve for V2. So I kind of did both in the same step here. So we have the equation rearranged. So this is what it's going to look like. Getting that T2 on the other side of the equal sign by multiplying it results in this guy here. Next, you plug in the values. So V1 is 4,000 liters. T2, the final temp, was 50 degrees. So we need to add that 50 to 273.15 because we need to get it into Kelvin. So that's the purpose there. Now in the denominator, we have the initial temp of 25 added to 273.15 to get that into Kelvin. The resulting answer is 4,340 liters. So the volume did indeed go up. So it looks like we most likely did it correct. I did round that, by the way, to get it to 3 sig figs, so that's why it's 4340. Next, we're going to look at the Guy-Lussac's law, looking at pressure and temperature. So in this problem, we have volume in moles remaining constant, and it's just the pressure and temperature that are changing. So they give us an initial temperature of 273 Kelvin, and they're saying that the pressure is increasing from 0.15 atm to 0.625 atm. So usually when pressure increases, it's due to an increase in temperature, because if you increase temperature, those molecules are going to move around a lot faster. If they're moving around a lot faster, they're going to hit the insides of the container more often, causing the pressure to go up. So we should see an increase in temperature when we solve for this. So plugging those numbers into the equation, solving for final temperature T2 here. So if we rearrange that to solve for T2, we get a value of 1,140 Kelvin. So yes, the temperature did increase quite markedly, actually. Next, we'll look at Avogadro's law. So pressure and temperature are kept constant for Avogadro's law. So basically the opposite of the Guy-Lussac law because we're using the other two variables, volume and mole amount. So in this question, we have a volume of a gas initially at zero point 0.5, or excuse me, 0.05 liters, and we have the amount of moles changing. So it's initially starting at 0.00065 and increasing to 0.0085 moles. So plugging those values into the equation, we're solving for the final volume. Now you can guess for this equation that volume and moles are proportional to each other, because if you increase the moles, what you're doing is you're increasing the amount of atoms, the amount of matter. And if the amount of matter and the amount of atoms goes up, you can guess the volume is going to go up too, because it needs more space to hold that new amount. All right, so rearranging this equation to solve for V2, we get a final answer of 0.65 liters. So did the volume go up? Yes, it did, because it started at 0.05 and went up to 0.65, which makes sense since we added quite a bit more matter. Let's try one more problem utilizing Avogadro's number. So in this problem, we have 5.50 moles of carbon monoxide occupying a volume of 20.6 liters. So we need to calculate the final volume once we increase the carbon monoxide up to 16.5 moles. So since we just have moles and volume, we're using the Avogadro's equation, solving for V2, final volume. So that's what we need to rearrange the equation, solving for V2, and then plug in the numbers. So kind of did it all in one step here. So rearranging the equation, solving for V2. This should be V2. We are going to multiply the initial volume by the final mole amount and divide it by the initial mole amount. So you can see those numbers inserted here to give us a final answer of 61.8 liters, showing us that when we increase the number of moles, we are indeed increasing the volume as well. So a recap on the laws that we just went over, Boyle's law and its corresponding equation, focusing on pressure and volume, keeping temperature and moles constant. Then you have Charles' law that keeps pressure and moles constant, focusing on the volume and temperature variables, remembering to change that temperature into Kelvin if it's given in degrees Celsius. Have a nice little diagram off to the right in ways to remember these equations coming from that base equation. Then you have the Guy-Lussac's focusing on pressure and temperature, and then Avogadro's, of course, will have the molar amount in it, and that will be in relation to volume. Next, we're going to look at a problem that used the combined gas law. So the combined gas law is going to have 3 of the 4 variables instead of just 2 variables like we saw with the other gas laws we were just looking at, Boyle's, Charles, Guy-Lussac's, and Avogadro's. So you'll notice here we have pressure, volume, and temperature on both sides of the equation. So for these types of problems, you're going to be given 5 out of the 6 variables, and you'll be solving for the 6th one. So looking at this, we have helium gas. So they give us an initial volume, an initial temperature, and an initial pressure for that helium gas. So that's our P1, V1, and T1. So when the gas is then compressed, they give us a new volume, V2, and a new pressure, P2, asking us to solve for the final temperature, which is T2. So we're going to rearrange this equation to solve for T2, final temperature. So it's going to look like this here. So in order to get that equation, what we did is we took T2 and we multiplied it on both sides of the equal sign so that we could get it up in the numerator since it's in the denominator. And then we took reciprocal of this P1V1 over T1 and multiplied it on the other side. So bringing T1 up into the numerator on this side, and then P1 and V1 into the denominator below. So lots of things happening. This is the hardest one to rearrange. So if you're having trouble with it, be sure to ask about it during class. So here's our rearranged equation. So now that it's rearranged, we can plug in the appropriate values. It might be helpful to make a list of knowns and unknowns to make sure that you're putting the correct information in for the correct variables. So you can see we have the final pressure on top with the final volume, and that is multiplied by the initial temperature that's already in Kelvin, so we didn't have to do a conversion for that. Then in the denominator, we have the initial pressure of 5 and the initial volume. So solving for the final temperature, we get a value of 375 Kelvin. So here's another one. Feel free to pause and try it on your own. So this is the combined gas law. Now, how would I know it's the combined gas law? By just reading it. Okay, well, for instance, look at what they're giving you. Okay, they're giving you a volume, a pressure, and a temperature. Then they are changing it to a new volume and a new temperature and asking you to solve for pressure. So right now we know that temperature, pressure, and volume are all going to be variables. So that tells me that it has to be the combined gas law because we have an initial and finals of the same variables. The only thing remaining constant is the molar amount. So we need to take the combined gas law equation, solving for P2, so rearranging the equation to solve for the final pressure, the new pressure. So when we do that, we get the equation shown here, P1 V1 T1 divided by T2 over V2. Next, we plug in numbers for those variables. You can also notice with the units, right, temperatures canceling, liters are canceling, and you're left with units of atmospheres, which is what we want because we're solving for pressure. So we get a final answer for a new pressure of 2.16 atm. So the last equation we're going to discuss in this section of the chapter is the ideal gas law. So for the ideal gas law, we don't have multiple of the same variable. So before we were looking at equations where pressure was changing, volume was changing, temperature was changing, moles were changing. Okay, so there was two of each variable. For the ideal gas law, there's only one of each. Okay, so it's all stuff we've seen before other than this R. So we have pressure in atm, volume has to be in liters, N stands for moles. Now the R, that's a constant, a gas constant that we use. And the gas constant we're using is 0.08206. So the units on that are liters, atm over Kelvin and moles. So as you can see, those make up the units of the other four variables involved in this equation. Once again, temperature has to be in Kelvin just like it did before. Now, when we're using the ideal gas law, we're assuming that the gas itself is ideal. So what are the criteria to make an ideal gas? First off, number one, molecules do not interact with each other. The second one, the volume of the molecules is much smaller than the volume the gas occupies, which that makes sense as well, right? The molecules are going to be smaller than the container they're in. Number three, all gases are compressible and in constant motion. Well, we know this to be true. We said that gases are easily compressible, and then they are in constant motion. They do continually move unless the temperature was to be lowered to a point in which they would change form from a gas to a different medium. Then the last one, speed increases with temperature. So we know this to be true as well. If you heat molecules up, they're going to get more energy and they're going to move faster. Often when you're using the ideal gas equation, you'll see the words in the question talking about standard temperature and pressure. And sometimes they don't even say the word standard temperature and pressure. Instead, they just say the gas is at under STP conditions or at STP. STP obviously standing for standard temperature and pressure. So what is the point of that? What are they actually giving you by saying that? Well, they're telling you that the temperature is 273.15 Kelvin. So they're giving you the value for one of those variables. Standard pressure then is 1 atm. So they have given you two variables just by saying STP. So let's try this out and calculate the standard molar volume of a gas at STP. So since they said STP, that means they gave us the temperature and they gave us the pressure. So to solve for molar volume, notice the units, liters per mole. So we rearrange this equation so that we're solving for liters per mole. So how we do that is by having the volume on the top, which is in liters, and the N on the bottom, which units are going to be moles. So liters per mole is the answer we'll get. To solve for the liters per mole, we take the constant 0.08206 multiplied by the temperature, which they gave us just by saying the letters STP, so that's 273.15 Kelvin, and then the pressure at 1 atm. Now when we rearrange that equation, plug in the numbers for that equation, you'll see the value that we get for molar volume of any gas under STP conditions is 22.4 liters per mole. Now notice the question itself. It just says of a gas. So this molar volume applies to any gas under STP conditions. So it could be hydrogen, oxygen, carbon dioxide. This value will be the same, the molar volume of a gas. Notice it's only occurring at 273.15 Kelvin, and that translates to 0 degrees Celsius. Let's try a practice problem using the ideal gas law. So looking at it, how would you know that it's the ideal gas law that you need to use and not one of the other equations that we've learned? Well, you have to look at all of the information they gave you, and sometimes it can be helpful to write a list of knowns and unknowns to get there. So how many moles of gas are present? So moles is the question mark, so N is the variable representing moles, and that's the question mark. They have a container with 1.54 liters, so that's going to be our volume. They give us a pressure of 1.82 atm, and then they give us a temperature. So notice they only have one of each variable, so it has to be the ideal gas law. If they had two volumes, two pressures, or two temperatures, then it would be a different equation. So writing down your knowns and unknowns, notice we're converting these degrees Celsius into Kelvin. Since we're using the ideal gas law, we'll also need to use that R value, that constant, and plug that into the equation as well. We're solving for moles, so we're going to rearrange the equation to get N by itself. Doing that, we come up with PV divided by RT to calculate N. Plugging in the corresponding numbers, making sure that you have converted that temperature, we get a value of 0.112 moles. Let's try another one, this time using the conditions of STP once again, but instead of solving for molar volume, we're solving for just regular old volume. So it looks like the only piece of information they gave us directly was the number of moles for value for N. But by saying STP, they also gave us the temperature and the pressure. So if I write a list of unknowns, STP, the standard temperature, is 273, standard pressure is 1, molar amount is 0.35, and then of course we have our good old R value, volume being the question mark that we want to solve for. So we're using the PV is equal to nRT, solving for V, meaning we need the pressure on the other side of the equation in the denominator. Then we can plug in our numbers, our values from our knowns and unknown list, and we get an overall answer of 7.8 liters.